Thank you very much. Nice to see that I have a supporter base here. It's good. If you guys want, there's a lot of space here. You can sit down. Before I start rambling about confidential computing, I want to take the chance to give the previous speakers a big round of applause. I think it's been great today. So, yes. My name is Joel Rangsmo. I've been doing IT for most of my life. When I was a mere boy, I started as a sysop or system operator. And for you young kids in the audience, back in the days, not everyone were engineers. It's good to know. And I built a lot of stuff. I think it's fantastic fun. But after a few years, I wanted to start breaking things. So I joined this fine gentleman over here and spent a few years at a consultancy company doing mostly offensive security. And breaking stuff is great, but I wanted to go back to my roots. So I applied for a job at a small cloud provider, and we had this great CISO at that place. And he was really excited about a lot of stuff, and one of them was this new thing called confidential computing. So I started looking into this slightly before I got employed there and during the time, and unfortunately that project never went anywhere, and we had a lot of other things to fix that were burning. I've since left that place, but the idea and the concept of confidential computing has still been rattling around in my head. And I don't know if any of you have tried looking into this, but I find it's like two great mountains. So on one side we have super marketing fluff, and on the other side there are like very scary mathematical formulas that make me very nervous. So what I will try to do today is take you into the valley where we can, as humans, understand this and like cut away all the marketing buzzwords. So by the end of this talk, I want you to have an idea what confidential computing actually is, how it can be implemented, and maybe most importantly, since there's a lot of offensive people in this audience, the problems with it, because there are quite a few, regardless what the marketing material says. So I will not be dropping any groundbreaking research or O-days today. But I will try to explain this in about 41 minutes. It's 64 slides, we'll see how it goes. I'm quite humble, but in this case, I like to look at myself as Jesus Christ. He died on the cross for your sins, and I have gone through the trauma of looking at all the marketing material to try to figure out what's actually in there. So, are you excited to learn about confidential computing? Yeah. What about you, white man in black t-shirt? Good. Everyone is in. Some housekeeping first. You don't need to take photos of the slides. If you dare, you can scan this QR code. It's not a WebView 0 day, I promise. All material is available under the Creative Commons, so if you have suggestions or corrections for me in this talk, feel free to drop them on the GitHub repo. I'm going to try to explain a lot of things, but I have 41 minutes left, so I will assume that you know a bit about, well, cryptography mostly. So you know what full disk encryption is, why that is good. You pretend to understand how X509 and the certificates work, and you know what asymmetric signing and asymmetric encryption is. You are also aware that Pass the Hash is not a song by Snoop Dogg, but rather an attack for... so some basics of cryptographic hashing. And I also wrote the guts of a Linux system. We will see if you need this or not, but it's good to be aware that there is a kernel, there is a userland, something is called grub, who knows? And besides these things, it's very good if you have a love for acronyms, because we will have a lot of them. And of course, a healthy dose of skepticism. We have a drinking game. I don't know why the picture is gone. Maybe I should try actually be connected to the internet. So since the bar is open, I took the liberty of dividing a few rules. So as I say, I will try to spare you from the marketing stuff, from the buzzwords. So if we reach a point where I accidentally say one of these words, maybe I have, what do you say, assimilated into the marketing cult, then you can shout drink, and I will try to comply. All consenting adults in the audience can, of course, participate. Okay, I am back online. Let's see, we do one of those, and maybe if I can find the right screen. There we go, thank you. Wouldn't want to miss my nice pictures. So, we can try this. AI cloud data. Thank you. It's also what I will do whenever I'm thirsty, so I may say some words accidentally. So, the elevator pitch for confidential computing, if you manage to find an engineer, get them away from the PR people, and maybe pour a few beers into their mouth, like I had the fortunate opportunity to do during the open source firmware conference last week. They may say something like, the great thing about confidential computing is that you can run workloads on systems without trusting the underlying infrastructure or provider to ensure your confidentiality and integrity. And this is not magic blockchain stuff, so they still need to... No one said drink. Magic blockchain stuff. So they still have to ensure that your system stays online. But besides that, we're good. Why is this a good thing? A rhetorical question. Of course, it's more money for Jeffrey Bezos, so everyone's happy. Joking aside, not all computers around the world are run and operated by Amazon. It may come as a surprise to some of you younger people in the audience. And the reason why people choose to not use the public cloud can be due to the fact that they have some sensitive information that they don't want to share. Maybe they don't think they're allowed to share it. We will not get into that discussion today. But if the trust paradigm would change, so we can run our sensitive things in the public cloud, well, there's a lot of money to be earned, potentially. I could pull some Gartner numbers out of my ass, but just let's call it a lot. And as a small regional cloud provider, it's actually quite scary, because you know that Amazon employs 1,000 security engineers, and you're sitting there trying to protect your system, so potentially it could even help the small guys. Buzzword, edge computing. So there are some imaginary workloads, usually talked about in relation to 5G and stuff, where very, very low latency is important. So think autonomous self-driving vehicles or something like that. And the way to get very low latency is to be, well, close to your user. So what they are envisioning is that in every single cell tower next to it, there will be a rack of servers that we can run things on, and that can like respond directly to requests coming in from clients. If you have any old freakers in the audience who've been like kicking up telephony boxes and things in the forest, you know that the physical security of these ain't necessarily great. So if we could run things on a system and be somewhat fine, even if someone went into the rack and actually started messing with our hardware, that would be quite neat. And I tried to come up with some, like, what are some offensive use cases for this? And there are probably many. One could be that you have some malware running, and you're looking for files or certain strings on the victim's system, but you don't want to like divulge what you're actually looking for. So if you could run things in an environment where they can't be sneaked upon, that could be quite neat. Also, this applies to your fancy machine learning models, etc. Tack. defense in depth. I mean, even if we don't believe that this is the silver bullet, a technology that will save us all, at least it would be nice to know that everything isn't necessarily doom and gloom if our host system is pwned. So when it comes to requirements, there is a very important thing I want to note here. So we need somewhere safe from the confidentiality and integrity perspective to run our things. But we also need some way to be sure that it is actually the case. So your provider saying that we take your security very seriously will not do it. So we need some other way to prove it. And there are a lot of options for confidential computing. Intel SGX has been around for 10 years or so, where we can run our applications in enclaves or trusted execution environments. The problem with SGX is that you need to kind of massage your application a lot to actually make it work. It's not like other development environments. You can't just take SAP and run it in an enclave. So what has changed during the last couple of years is that the CPU vendors have started introducing option where you can run a full virtual machine inside a trusted execution environment. So not just your custom-built application. And this is cool because we can basically keep doing things like we've always done with the addition of some magic confidentiality and integrity protection. At least that's the marketing pitch. And I will not have time to talk about all of these. So what I will focus on today and that I've been looking at during my research is AMD's SEV, or Secure Encrypted Virtualization Technology. And before we get into that, how that works, we will talk about some building blocks, because we will need to know these things before actually being able to understand how SEV actually works. So I will do a speed run of some of these familiar names of technologies, and by the end of it, I hope that you will be able to piece together my reasoning and see why knowing about this is relevant to understanding confidential computing. And there will be some shortcuts and simplifications. I don't have as nice diagrams as Joris yesterday. There are no animations here. But two important things to keep note of. Up in the left corner, we have the power button. You press it on your physical machine. And by the end, you hopefully have a happy user. And there are a few steps happening in a traditional boot on a UEFI system. So for you old people, if UEFI is a scary term, you can just search and replace it with BIOS. So first, something happens. Depends on the platform, the vendor. I call it dark magic in this case. Then we load the UEFI implementation, a component called the FE stub, because a bootloader such as Grub, at least historically, haven't been able to be directly booted from UEFI. Then from Grub, we start getting into more familiar territory. So we're going to launch a Linux kernel. We're going to have an initial ROM disk. I will call it initrd from now on. And we also have a command line that we will supply. You are probably aware of this. If you start a Linux system, specify init equals /bin/bash, you get a root shell when you boot the box. After that, some fun things happens depending on your system configuration, but most likely, if you're a gentleman like myself and use full disk encryption, we will decrypt and mount that file system. And this is not super great from a security perspective, because if any of these components are compromised, that will affect the security of the whole system. And generally speaking, the earlier component is affected by a security flaw or backdoored or whatever, the harder it will be to detect. So even though Richard Stallman got very sad, something called Secure Boot was introduced, sometimes called Verified Boot on platforms that are not PCs. And here we basically use cryptographic signatures of the components. So in the boot chain, every component is responsible for validating the authenticity of the next component in the chain. And on a Linux system, this typically breaks down somewhere after grub, because maybe you mesh or have a signature of the kernel, but not the command line, then not the initrd. So it's not perfect. Cool kids these days use something called UKIs, or Unified Kernel Images. And there we basically take the Linux kernel, the FE stub, and the initial ROM disk. And we mash that together in a PE executable. So yes, UEFI executes P executables. So we have linux.exe running here. And we can cut away a lot of the problems in the chain that may otherwise cause problems. So it's a little bit less brittle. When you have a lot of key materials to sign all these things, a good practice is to put them in a HSM. Most of you probably already know what this is. You probably also have one in your pocket. But for the sake of this presentation and the things I will cover next, I have a short slide about them. Feel free to read if you so like. It's basically a dedicated device for performing cryptographic operations. And as a general rule of thumb, if you put a secret in a HSM, you cannot get it out again. So an attacker with access to the HSM can force it to sign and decrypt data, but they cannot run away with the key and sign arbitrary files, unless it's broken, which happens. The next thing is measured boot that I want to talk about. And you can use this together with secure boot, but the problem with secure boot is that you don't know exactly what you're booting on your system. You know what you're booting is signed, and it's signed by a key you have in the system trust store, but not much more than that. So maybe you don't want to boot Windows, even though it's in the trust store. And measured boot can help us here. MC talked about it yesterday, and in this case, instead of just validating cryptographic signatures of the next component in the boot chain, we take a hash of the component, and we store that in a hash chain. And I've been trying to think of different ways to explain this, so I have this very pedagogical slide here for all you visual learners. But the cool thing about a hash chain is that if we know the last link of the chain, the hash of the last component after measurement, since the chain or the measurement of that component includes all previous hashes, there should only, not theoretical, but in practice, be one combination of previous components and an order to them. So in essence, we have an append-only data structure. So a component can lie about future measurements, but not past ones. But we need somewhere to store this, and that's where TPMs comes play. So trusted platform modules, they're like traditional HSMs, but with a few more features. There are a lot of them. One thing that's noteworthy in this context are the PCRs, or the platform configuration registers. So we can basically put a measurement into a PCR, and the TPM will, from that, build a hash chain. And we can use some neat things with this. We can measure the system and say that we will not release a key, a symmetric key that is stored in the TPM, unless the value of these PCRs are X and the user has supplied a password or biometric or whatever. And there are a lot of problems with the TPMs that I don't have time to go into, but for the sake of this presentation, let's just imagine that they work for 1 second. Another cool thing TPMs can do is, well, what's called attestation. I don't know if any of you saw my talk during the SecT Spring Pub. I talked about YubiKey's key attestation. It's somewhat similar. So when the TPM is manufactured, asymmetric private key is burned into it. We call this the endorsement key. The vendor then signs a certificate for the public key associated with the endorsement key with their CA. And using this endorsement key, we can derive an attestation key. And the attestation key can then be used to create signed reports of the state of the TPM. So like what's in the PCRs, etc. And granted that we trust the vendor's certificate authority, we can validate these measurements. So we can say that with some certainty, these measurements were actually, or this report actually came from a genuine TPM that we trust. So we can use this to do something called remotely attested boot. It basically builds on the measured boot concept, but instead of being happy with saying, yes, we have checked all the hashes, it's all good, we can go out to a remote party on the internet that I will call verifier from now on, something that holds on to keys, decryption keys, API tokens, or whatever than that. And we can ask it for one of those. So maybe we want to unlock an encrypted disk, or we want to access the murder robot that will chop off your fingers if you use it incorrectly. And we do this by asking the verifier for a secret. It will return a nonce, a challenge. We will ask the TPM to produce one of these attestation reports that it will sign with the values of the PCRs included. And we will also ask it to include the nonce in the report. The verifier can then look at this, and granted that it trusts the TPM vendor's CA, we can determine that this report is genuine, and we can then return a secret to the client. And this is kind of cool, I think at least, because we can be somewhat confident that the system is in a state that we find acceptable before letting it harm people or process private data or whatnot. And as I said, the TPMs are not problem-free, so for the sake of the following presentation, let's assume that they actually work. Like the quality of TPM crypto, it makes OpenSSL in 2012 look like prime software, so. Big data. Thank you. Another cool thing we can do is we can extend this beyond the boot process. So in Linux, there is something called the IMA subsystem, and that can perform continuous measuring of process execution and things like that into the TPM. So if at one point the system starts executing netcat when we don't expect it to, we can see it in the attestation reports and maybe shut it down or whatever. If you find this interesting, there are two projects I want you to check out. Keylime is one of them that actually allows you to do this in a more or less end-to-end example. And then there's also the System Transparency project, which do a lot of cool things related to attested computing. So, back to SEV. There are many different versions. It was launched with the first generation epics back in 2016. Since then, there have been a lot of vulnerabilities. I mean, new versions that improve security and protections. And when I, from this point, say SEV, I mean SEV-SNP, which is the latest version of this technology. What does it provide? What can we do with SEV-SNP? We can start virtual machines that will get their own encryption key, magically, transparently in the background, associated with the CPU context. And it will protect the RAM or the system memory used by this VM using encryption, and also encrypt the CPU registers. And it's designed to let you run virtual machines on a host without trusting the hypervisor or the operator, even if they have physical access. This doesn't always work. It's a bit of foreshadowing, but we get to that point. Most of this is handled by another processor on the processor called the secure processor. It's known by many names: ASP, PSP, SP. I will mostly use the acronym SP from now on, but if you see this in documentation, it's all the same thing. And it's actually a little ARM v7 core on the main CPU die that runs its own operating system, which is started before the main initialization of the x86 processor. So in tandem with the CPU, it provides these features that SEV claims. One important thing is that this is quite similar to a TPM, so it has an endorsement key burnt into it. So the things that we learned about how TPMs work can largely be applied to the SP. So we want to start a confidential virtual machine. What happens? The security processor, or secure processor, sorry, generates a new key for transparent encryption, and it associates that with the guest CPU, virtual CPU context. It then performs a measurement of the initial guest state, so a bit similar to how a TPM do if we feed the data into PCRs. It then generates another key, and it places it into a known location in the confidential virtual machine's private memory. So the SP knows about all encryption keys, so it can do that. And when the guest boots, it can look at this known page, take the key from that, and then use it through encrypted and authenticated communication with the secure processor. So the guest cannot talk directly with the SP, but it can do so through the hypervisor, which is untrusted, but we use encrypted authentication to protect that. And when we, as a guest, ask the secure processor to provide an attestation report, we get a bunch of interesting data. We get the product ID or product name slash Epic CPU generation. We get a chip unique identifier. We get a digest of the initial guest state called the launch measurement, or the launch digest, LD for short. We can tell if various security features are enabled, or security adjacent features. So maybe we're paranoid. We think that this concept of SMT, or simultaneous multi-threading, maybe was not the best idea. We put the state of is hyper-threading, basically, enabled in the report. And we then take a bunch of version numbers of firmware components, so like the secure processor bootloader, the CPU microcode version, etc. And the thing that these have in common is that they are the TCB of the SEV feature, so trusted compute base. So you need to trust this software explicitly for SEV to work. And note that I say version numbers here and not hashes or digests of the firmware. This will come into play later. Of course, relevant question, what is measured? When we start a confidential guest, SEV only measures the initial guest state and the virtual firmware that we load into it. This is typically OVMF, or Open Virtual Machine Firmware, I guess. It's based on Tiano Core's EDK2. So if we have any UEFI devs in the room, they will be familiar with this. But it's basically UEFI for virtual machines. So that is the only thing we measure. We don't measure the guest operating system actually launched, the Linux kernel, etc. So in the SEV world, that responsibility to secure the following components in the boot chain is left to the virtual firmware, or VFV as I call it here. And there are a few approaches to do this somewhat securely. We could, if we're using UKIs, so 1P executable containing Linux kernel, initRD, and command line, just hard code a digest of that into the firmware, so the firmware is only allowed to boot that. We could use secure boot. So we could say in the virtual firmware that this CA, my company's CA, is the only one that should be trusted. So in that case, we don't know what software we're running in the what operating system we are running in the confidential VM, but at least we know that it's signed by a CA we trust. Or we can go for the approach that I will be using, where we basically inject digests of the relevant components into the virtual firmware's memory before the measurement is executed. There is a fourth approach that I haven't listed here. I call it the YOLO approach. You basically don't do any validation. It seems to be what most people do out there. But let's try to do this as it's supposed to be done. When the secure processor generates an attestation report, it signs it with a key that is derived from the one that's burnt into the chip. And these are called V6, or version chip endorsement key. And this is actually not a bad idea. So they have seen all the previous mistakes that others have made, and they themselves have made in earlier versions of SEV. So we don't want to end up in a situation where everything is like you have to throw your CPU in the garbage if a vulnerability is identified in any of the firmware components in the TCB. So what we instead do is that we take a key derivation function, we put in the chip unique secret, and then the various version numbers of these firmware components. So essentially, we have a new signing key whenever we change one of those components. And this is supposed to be done in a very protected part of the secure processor, so basically on the secure processor's secure processor. We will see if that actually works. But this is also good because if we're then validating report, since the key used is based on the version numbers, it's not supposed to be able to at least spoof which firmware version it's running on. To validate this report, we will need to take a trip onto the World Wide Web, go to AMD's key distribution system. It's an HTTP service. And from this, we can fetch a certificate matching the versioned chip endorsement key. So since we include a chip unique ID in the unverified attestation report, and also version numbers for the firmware components, the TCB firmware components, we can go out to the AMD KDS and ask it to provide a certificate that is valid for that exact combination. This is the most common way. There is another path called the extended attestation report, and that's basically where the guest provides a VSEC matching the one that's used to sign the report. But since the VSEC is signed by, the VSEC certificate is signed by AMD's CA, we can still trust it even though it comes from a guest that we don't know yet if we should trust. If we want to play with SEV-SNP, we need a quite expensive CPU, third or fourth generation EPIC. Not the most easy to come by, at least if you're cheap like me. And we also need some exotic BIOS or system settings configured. So you will not just be able to rent any server from a dedicated hosting provider and do this. It will need to be set up in a quite meticulous way. And a lot of these changes required to actually use an end-to-end example of SEV-SNP aren't yet mainlined in the various open source projects. So we need to build our own Linux kernel, our own QEMU, that's the quick emulator, what we use in Unison with KVM to run virtual machines, and OVMF, which I previously mentioned. So this is the virtual firmware or virtual UEFI running in a machine. And we actually, to make it work, need to patch the patches a bit, but I have thankfully done that for you. I was thinking of renting a machine or buying a machine, but as a self-employed consultant, I'm frugal, so instead I spent way too many hours on automating this. So in the resources archive associated with this presentation that you can find using the link, there are a bunch of Ansible playbooks and some make files. And if you run this, a bare metal host would be allocated in Walter's cloud. It will configure a bunch of things for you. It will build the required components, so you can get playing in minutes or hours, depending on what your performance is to compile the Linux kernel, etc. And personally, I find this quite neat because it allows anyone with a few dollars to actually play with SEV-SNP instead of having to buy all the required hardware. Just remember to shut these instances down when you finish playing, because they cost like $1.50 an hour. So I don't want to ruin you, and don't blame me when that happens. Big data. So in this lab setup, we have your computer. It's where we run the automation, where we by default build the various components. We use it to configure 2 remote servers. I call them the hypervisor. It's a bare metal instance running with a 3rd generation Epic and using Qemu to execute confidential VMs. And then we have the verifier. And that basically looks at these attestation reports, and if deemed trustworthy, it returns a secret to the guest. And the guest operating system is super minimal. It's basically just a Linux kernel and a super small initial ROM disk. And in this initial ROM disk, we have a shell script, which I will show you in just a moment. But as an advice to anyone liking building small embedded Linux system, check out the uroot project. They make a wonderful tool for this. And this is my award-winning shell code, or bash code, maybe I should say, that we will use in the following demo. Maybe it's a bit too small. I can zoom in on 2 relevant parts. The first, we acquire some network configuration from DHCP. We need this so we can reach out to the remote verifier. We then also read the remote verifier's address from SMBIOS, so you can supply this when you start running the machine. And this is so we don't need to hard code it into the build, so we can actually do building of all the relevant components before we start paying for infrastructure in the cloud. And the second part, this is where the juicy magic happens. So we use a tool called KBS client, and this will go out to the verifier, ask the secret, get a challenge back, and then perform an attestation report. And if that succeeds, it will just print it to standard out. And then, since this is a confidential guest, we don't want to reveal our secret, so instead just produce a hash digest of it that we will print to the screen. But we need, to be able to verify this attestation report, we need to know what the expected launch measurement of the guest is. And there are a few tools to do this. There's one Python implementation. And here we say, this is the OVMF we want to measure. These are the kernel, initrd, and command line we want to include. And then we also have to specify which type of virtual machine monitor is it that we will be running this VM on. Because as it is today, this is improving. All hypervisors put these things in memory in a slightly different way. So we need to know which way it will be done so we can actually validate the measurement. And this tool spits out base 64 of the launch digest. So we can copy-paste that into the policy of our verifier. If you have ever played with any cloud-native projects, tack. I need you guys. It's good that you're awake. This is written in a language called Rego. The idea is that we decouple authorization decisions in our application from code, and we can instead write them in Rego so we can do whatever we want. So what we're doing in this policy to determine if we should actually give a secret to the guest is that we check that the resource they're trying to access is this specific secret called my secret. We check that the attestation report was provided by an AMD SEV-SNP compatible system. We can use this with Intel VTD and other solutions for confidential computing. We then check that the microcode of the processor is at least version 210. So maybe there is a vulnerability that we know about in a previous one. So we don't want to trust any attestation reports produced by those systems. And then we check that totally secure memory encryption. That can't be right. Well, that memory encryption is applied for the whole system and not just the guest. And this is just an example policy, but we can do a lot of these things. And on the last line, we actually check that the guest measurement that the secure processor has derived is the same one as we got in the previous slide when we did this on our local machine. There is a technology or a technique where you can, instead of like hard coding digest, you can bundle something called the ID block inside the measurement reports, and that you can sign. So you can say that in this signed block, let's say that Ubuntu, for example, would provide virtual machine templates for this. They could say that these are acceptable launch digests, and if you trust Ubuntu's key, then you could instead check for that in this policy. So when we start a guest, using make, of course, to hide all the gross Ansible magic in the background, it will start booting the machine. We will then see output from our script that I just showed you. That's in the init RD. We will do some pre-flight checks. We will configure the network using DHCP. And we will read the verifier host from SMBIOS. And now, the reveal. Will this actually work? So we got a secret from the verifier, meaning that at least it accepted our the attestation report, and it complied with the policy we just configured. So we get the hash here, and do we think it's the correct one? Can I get a drum roll? Yes, of course. So we can do this locally as well. We see it's the same, the same digest. I am running out of time, so I will skip this slide. You can read it if you so please at your own leisure. But as I talked before, everyone has put init equals /bin bash in the kernel command line, so can't we just do that ourselves, run KBS client and steal the secret? Or perhaps modify OVMF to leak it? And the answer should at least be no, because that would affect the launch measurement of the guest. There are a lot of funny things happening in SEV-land, some which I've excluded in the scope of this presentation, and I have 2 minutes left, so I will not get into this. But if you want to play with it, maybe, let's say, a year from now or so, I think SUSE Linux will be the best option, because they have worked close with AMD to implement this, so even before they are mainlined in the Linux kernel, etc. Everyone in the room hopefully asks, yes, this is cool, but what's so problematic? I thought this was a security conference, it's not a sales pitch. And a big problem is that we need to trust both the CPU and the secure processor. And these are closed source components, they are proprietary. We don't know what's going on in there. AMD is doing some work to open some of these up. They have done a code dump of a small part of the SP code, but you cannot build it. They don't provide any instructions of that nature, and you also cannot flash it, so who knows what you're actually running. And these components that are in the SEV TCB are extremely important, so it would be a shame if there were any vulnerabilities in them that could be used to disclose the encryption key for the guest memory. And there was such a flaw that was reported back in 2021. The paper is called One Glitch to Rule Them All. I recommend you all to read it. A cool thing that they showed was they were actually able to break this versioned ship endorsement key system, so they could produce valid keys for any firmware version, more or less. And this is sad because it breaks the whole promise of the system. And if you can produce this for future versions, well, then you cannot fix the flaws in future versions. My favorite part about this paper is the section in the introduction where they've reported this flaw and AMD were like, okay, well, it's going to affect our sales numbers, so let's not look too closely at this. And Intel is not much better. I don't want to shit talk AMD. They had this fine flaw that was released in a tweet about 2 weeks ago, where the fuse zero key, basically doing the same things as I've shown here, was also able to be extracted. The AMD KDS, or key distribution system that I mentioned, it's a single point of failure. So if you cannot reach it, if it's down due to denial of service or for whatever reason, you cannot get these new VSEC certificates, so you cannot validate attestation reports. Or maybe AMD chooses to embargo your country or whatever, and suddenly you cannot actually prove that or verify them. Another thing that I find funny about this is that to be able to produce these certificates, they need to get a public key matching the private key that was used to sign the goddamn thing. And the VSEC is derived by version numbers and a ship unique secret. So they must keep it on their side. So AMD stores all unique ship secrets. And so if NSA were to knock on the door, who knows, they may give it to them. So if I was GRU or North Korea, I would not migrate to AWS just yet. And the guest attack surface is huge. I mean, we're talking about running the Linux kernel and OVMF, which are like 20-plus-year-old software, in a machine that is not supposed to trust its host. So while memory and CPU registers are encrypted, the hypervisor is still responsible for emulating all devices like block devices, network cards, etc. And I dare to say that these systems were not designed with this use case in mind. So would you trust a malicious attacker to just randomly jack in hardware devices into your host? I think not. There are some efforts being made here by Intel, but it's a very, very long road ahead. I am running out of time, so I will skip these slides. But what I can say briefly is that we have introduced a lot of complex code to be able to do this in the Linux kernel and other supporting components. So the risk of a guest to host basically a hypervisor breakout bug has increased significantly, I would like to say. And hopefully by now, I hope you understand that we cannot simply lift and shift things. We need to set up a verifier. We need to adapt our CI/CD pipelines to actually like calculate the launch measurements, etc., etc. So this is no easy task. Maybe some of these things are good. I mean, I still think that a tested boot is a nice thing, but it's not something that can be done in a day. So you will have to keep your basement data center running for just a little bit longer. So should you use, or rather should you rely on these confidential computing technologies? I think not yet, unless you have a very, very specific use case. And since you will need to do a lot of changes for what I would argue is a bit unclear benefits, maybe you could spend that money wiser elsewhere. I mean, no one has an unlimited budget, so unless you really need this for your use case, I don't know, hire a company to do a pen test or something instead. There are some people I want to thank. Two fine German gentlemen who have helped me a lot in understanding these things. I think I will have a conversation with them after this talk where they will politely yell at me for all the things I got wrong. That's okay. 8x86.lol. It's a great blog that I recommend you to check out. It writes a lot about confidential computing. And of course, the SEC-T crew for letting me stand on this stage and ramble, and all of you who have been listening. So, as I said, if you want to get the slides, you can either copy-paste that link with your eyes or scan the QR code. And if you want to chat, there is my email. I'll be happy to talk to you after this presentation. And yeah, if you want help with building something cool and something reasonably secure, reach out. If you want to join another cool party after SEC-T, me and some friends are running internet, offline computer party. So that will be a lot of fun, I hope. So thanks for listening, and see you in the bar.